So we're going to do an example problem that goes over interference fits and how to calculate the stresses associated with them. So in this case, we have an aluminum cylinder, okay, that has an internal diameter of 150 millimeters. It has an internal diameter of 100 millimeters. All right. Then we have a stainless steel cylinder that has an external diameter of 100.20 millimeters, and it has an inner diameter of 50 millimeters. Okay, we know that the elastic modulus is going to be 190 gigapascals, and then the Poisson's ratio is 0.3 for steel, while for aluminum, we know that the elastic modulus is going to be equal to 70 gigapascals, and the Poisson ratio will be equal to 0.33. Okay, so all right, so for our equations, we need to first solve for the stresses and strains within our system. So what we're going to do here is we're going to define um, our pressure. So that's the first thing we need to do is define our interface pressure. So in order to do that, we'll need the following equation. So this equation gives us an equation determined for the interference pressure at our interface here. So this is the pressure at this interface. Okay, so we know so the rest of the variables we're given the outer element material properties. This is for aluminum. This is the inner material properties. This is for steel. Um, and then we have or I should say stainless steel. And then we have the inner and outer diameter. So C is equal to, so you can use, these are inner and outer radiuses, but you can also use diameter in these equations as well. So you can use diameter or you can use radius. Do not use both in the same equation. So um, so we have the inner and outer diameter for steel and for aluminum. And the only thing that we don't know in this equation is delta. So delta, if you remember, is equal to the diameter of the inner cylinder. So that's going to be equal to 100.20 millimeters minus the inner diameter of the outer element, which was equal to 100 millimeters. Okay, so what we end up getting is 0.200 millimeters, which is 0.2 times 10 to the minus third meters. Okay, so if we plug in all of these terms into all of our this equation here, we end up getting a pressure value of 40.78 times 10 to the sixth newtons per meter squared, okay? Or 40.78 megapascals. Okay, um, so what we can then do is we can find our stresses, um, our we can find our stresses for our outer element and for our inner element using sigma theta. All right, so um, so for the inner element, or sorry, for the outer element, and then for the inner element, we're just going to use equation So we're just going to use the following equation for the tangential stress. We're just going to plug in our values for our outer and our inner element. So for the outer element, Pi in this equation is going to be equal to P, all right, and PO would be equal to 0. All right, the inner and outer radiuses are all given. All right, so we can use, we can also just use the whatchamacallit. So we can use the diameters because that's what's given to us in this problem. So we'll use the diameters. So if we do that, what we'll end up getting is we'll get the pressure P, which is 40.78 times 10 to the 6th newtons per meter squared, times the inner radius squared, which would be, or the inner diameter squared in this case. We can use 0.100 meters squared, minus the outer pressure is 0, minus the difference between the outer and inner pressure. So the inner pressure was equal to P. So we would just get the outer pressure be 0 minus the inner pressure, which was P, times the outer radius times the inner radius divided by the radius squared. So the outer radius and the inner radius would be the inner radius was 100 millimeters, and then the outer radius was 150 millimeters. All right, and then we divide by the difference between the outer and the inner radius. So 0.150 meters squared minus 0.100 meters squared. Okay. All right, so we can do the same process for the inner cylinder. All right, we would just get, in this case, our inner pressure would be 0, and our outer pressure would be P. All right, so we would get minus 40.78 times 10 to the 6th newtons per meter squared, times the outer radius, which would be, in this case, would be 0.10 meters, millimeters, or 0.10 meters squared. Then we would get a minus 0.10 meters, so which would be the inner radius times the so it would be 0.10 meters times whatchamacallit. So it would be 0.10 meters times the inner radius, which would be 0.050 meters, divided by the radius squared, times the external pressure minus the internal pressure. So the external pressure would be 40.78 times 10 to the 6th newtons per meter squared minus 0. All right, and this would be equal to 0.150 meters squared minus 0.100 meters squared. Okay, so that is, sorry, this should be 0.100 minus 0.05 meters. All right, so if you evaluate these two equations, all right, for the outer cylinder, the maximum stress would occur at R is equal to 50 millimeters, or where the diameter would be equal to 100 millimeters. All right, and that would be equal to 106 megapascals. For the inner cylinder, all right, we would get minus 68 megapascals, and we would get, and that would occur at the inner radius. So So R is equal to 25 millimeters, or the diameter of 50 millimeters. Okay, um, and I should say this should be not the radius squared in these equations. These should actually be the diameter squared. All right. So if you did that, you get these two values for the radial tangential stresses in the outer element and the inner element. Both occur at the inner radius of the cylinders, um, and you get in the outer element you get a tangential stress, which makes some sense because it's being expanded, and then the inner element is being compressed, so you get a compressive stress.